Hey guys, here we go on part 3 of our unit about solutions. This one is about colligative properties. Here are some of the things we'll talk about. We'll just figure out what colligative properties even are, and there's 3 different types that we're going to deal with. So what are colligative properties? As it says here, the properties that depend on the number of solute particles in a solution. So the more salt or sugar or antifreeze or something that you put in some water, what it's going to do, it's going to affect these 3 things here. These are our 3 colligative properties. One is it's going to lower the vapor pressure of a solution. The other thing it'll do is increase the boiling point. So you put some salt in some water and your boiling point goes from 100 to something greater than 100. And also freezing point depression. That's the third one. If you put some salt in water, it's going to cause the freezing point of water to be below 0 degrees. So you have to remember these base numbers here. Freezing is 0, boiling is 100. This is why we add salt to our roadways, which I'll explain. So here's how this works. First we'll talk about vapor pressure and boiling point, because they're both related to the same reasons. So here's a beaker of plain old water. What you have to remember is there's atmospheric pressure pushing down on us all the time. This is atmospheric pressure. So when water's here, it's bouncing around. When it has enough energy to overcome the atmospheric pressure, it jumps out into a vapor state. So this is what evaporation is all about. It needs enough energy to overcome atmospheric pressure. Over here, we have atmospheric pressure also. But this time we have all these little salt particles or some sort of solute particles in here, the red ones. What happens is they hinder the water molecules from escaping into a vapor state. Notice how this one's trying to go up. There's a salt in the way, or salt ion, and it's going to bounce off. It's not going to be able to get out. So this is what we mean by vapor pressure lowering. Water has a very low vapor pressure. If you squirted out a bunch of water onto the table, it would take hours and hours or maybe days to evaporate. If you took something like acetone and squirted it on the table, acetone evaporates in several minutes. That has a very high vapor pressure. So that's what vapor pressure really is about, is its ability, a solution's ability to evaporate. So by adding salt particles, solute particles, it hinders this evaporation. Works for boiling also. Same thing, if you put a bunch of salt in some water, the water molecules have a harder time trying to escape. So what you have to do is you have to crank up the heat, this is a flame, to make it hotter, to give the water molecules more energy so they overcome the salt particles that are in their way. So this is why the boiling point will increase when you put salt particles in a solution. Freezing point works the same way. Here's a plain beaker with just some water, and you're cooling it down, and what ends up happening is the water molecules, as they get colder, they start clumping together and they form ice cubes, right? Here's like an ice cube. But if you put a bunch of salt particles or solute particles in here, the salt particles get in the way and hinder the formation of ice cubes. So now you have to cool this down even more to try to get it to freeze. So the whole thing about colligative properties is these solute particles get in the way of what the solution molecules are trying to do normally. So as mentioned in one of the first slides, colligative properties depend on the number of solute particles. The number, it depends how many particles are in the solution. So let's say we take a mole of sugar, which are covalent, we take a mole of sodium chloride, and we take a mole of calcium chloride. Anything that's covalent doesn't turn into ions. So if you have one sugar molecule, you're just going to have one sugar molecule floating around in the water. That's one particle. if you have one sodium chloride molecule that you drop in here, what's going to happen? It's going to split up into sodium ions and to chlorine ions. So you're going to have two different particles floating around. One of these will be sodium. One of these will be chlorine. So this is two particles. So here you have two particles, here you only have one. This is the sugar. Sugar does not ionize, so it's just going to be one particle. Say you have something like calcium chloride. This is going to split up into three particles because you have one calcium and then you have two chlorines. One calcium, two chlorines. So you have three particles. So this is why they use calcium chloride on streets instead of table salt. This changes the temperature of the water much more than something with less amount of particles. And it will have more of an effect on the vapor pressure, on the boiling point, and the freezing point. So which of the following would lower the freezing point of water the most? What you have to ask yourself is which will produce the most particles in solution. So if you have something like potassium fluoride, this is going to break up into potassium and to fluorine ions. So this would be two particles. Sodium chloride would also break up into two particles. Magnesium chloride would break up into three particles. You'd have one magnesium and two chlorines. This is a total of three particles when dissolved in water. And this is sugar. Because this is covalent, remember there's no metals here, so that's how you know it's a covalent compound. These guys here are all metals, they're ionic, so these break up into their ions like I showed here. But anything that's covalent only has one particle. They do not form ions. So anytime you see anything with no metals, usually things like sugar, you're only going to get one particle. So which is going to affect the freezing point of water the most? This one, simply because it has the most amount of particles when you drop it into that water. Let's look at the calculations involved with this unit. This is our main formula up here. Delta T equals KMI. So delta T is the change in temperature, and that's typically what we want to calculate. K is called the boiling freezing point constant, and it's simply these numbers. All you have to do is plug these numbers. If it's a freezing question, KF, this is for freezing. You plug in this number, and B for boiling, you use this for boiling problems. There is no calculation for vapor pressure, so we're just going to really be sticking with boiling and freezing points. Molality, this is a new formula for us here. Here it is, and this is little m. Notice the little m. Before we did molarity, which was big M, which was moles per liter. This is moles per kilogram. This is done by mass. So little m is kind of like molarity, except we're dealing with kilograms of solvent. Still moles, but kilograms instead of liters. And then ions, here's the factor that we were talking about with the number of ions. The more ions, the more drastic the change in temperature is going to be. So something like NaCl is going to have 2 ions. Something like CaCl2 is going to have 3 ions. So you would plug these numbers over here for ions. So let's do a problem. Here's a typical problem. This is very basic. So what is the new freezing point of water if 10 moles of NaCl are dissolved in 2 kilograms of water? So here's our formula. We're trying to solve for the change in temperature. It asks us what the new freezing points are going to be. Because this is a freezing question, we're going to use KF, which is 1.86. This is K. M is going to be moles per kilogram of solvent, and in this case we have 10 moles. 2 kilograms. And then I, because we're dealing with sodium chloride. 1, 2. There's 2 ions. There's your I. All right, so let's clean this up a little bit. So we have 1.86. 10 divided by 2 is 5 times 2. Simply multiply these three numbers together, 18.6. Now, this is the change in temperature. This triangle sign, it means change. Because this is a freezing problem, what is the normal freezing point of water? I hope you said 0 degrees Celsius. So because freezing point is a lowering colligative property, that means it's going to be lower than 0. So all you do is you take this number and you subtract it from 0, and you're going to get negative 18.6. This will be the new freezing point of water. 10 moles of salt dissolved in 2 kilograms of water. This is what the new freezing point would be. So you can see how putting salt on our roads is very useful. All right, let's take another example here. What is the new boiling point? This time we're doing a boiling point equation. If 3.5 moles of calcium chloride is added to 500 grams of water. So a couple things here. First is a boiling problem. So our KB boiling is going to be 0.512. That's our K. Little m is going to be, I'm just going to kind of do it this way. Little m is moles per kilogram of solvent. So we have 3.5 moles divided by 500 grams. This has to be in kilograms, so you have to convert this. 500 grams, let's do a little dimensional analysis. There's 1,000 grams in 1 kilo. So this would be 0.500 kilograms. That's what goes down here, 0.5. All right, don't put the 500 grams. This unit for molality is in kilograms on the bottom. So 3.5 divided by 500. And the final thing is I. How many ions do we have here? Here's 1 calcium. There's 2 chlorines. So we have a total of 3 ions here. This is our I. All right, so now let's plug everything into our formula. Change in temperature equals K. This is a boiling problem, so we're going to use the 0.512. Molality, little m, right here, moles per kilogram. We did this calculation, 7. And then our ions is 3. Delta T equals KMI. Multiply these numbers together, comes out to 10.7. All right, so this is the change in temperature. It changed by 10.7 degrees. By adding 3.5 moles of calcium chloride into 500 grams of water, it's going to change the boiling point by 10.7 degrees. But it says, what is the new boiling point? So what's the old boiling point? The regular boiling point of water is 100 degrees Celsius. Because boiling elevation is the colligative property. That means it's higher, it goes higher, so you add 10.7 to the 100. So now our final answer is this, 110.7 degrees. If you add 3.5 moles of calcium chloride into 500 grams of water, that water is going to boil at 110.7 degrees. Same type of problem, but different things that you might run into. So here's another one. This time we're using grams. Grams, you know what that means. Grams equals molar mass times moles. So we're probably going to need that formula in here someplace. So this is a freezing question. You have 500 grams of sodium nitrate is added to 900 grams of water. Let's see what we have here. Delta T equals KMI. This is a freezing problem, so our K is 1.86. M is molality, so we have moles per kilogram of solvent. So what do we know? Here's our solvent, it's water, so 900 grams, we have to convert that to kilograms, so you just divide by 1,000, so this is going to be 0.900 on the bottom. But how about moles? What are we going to do about moles? How do we get moles? We get moles from the fact we have 50 grams. 50 grams equals, what's the molar mass of sodium nitrate? It comes out to 85 because I did it before. So 85 goes up here, times moles. Solve for moles, 50 divided by 85. We're going to get 0.59 moles. So that's going to go here, 0.59. This is moles, 50 grams converted to moles is 0.59 divided by the 0.9 kilograms, and little m is 0.65. So here we put that 0.65, 0.65. That's our little m. We had to do this calculation to get that. And finally, how many ions are here? All right, so this is a little trickier. When sodium nitrate breaks up, you got to remember nitrate is a polyatomic. So you're going to get Na, and then you're going to get NO3. The polyatomics stay together, so technically here, this is only two particles. The Na is one, the NO3 is the other. So our I is going to be 2. So be careful with those polyatomics. They count as one. If there was a number out here, say there was like a 3 here, then that would be 3 NO3s plus whatever this one, then that could be possibly 4, but be careful of that. Multiply these three numbers together, comes out to 2.4. Okay, this is our change in temperature, but this is asking for freezing. We know the regular freezing point of water is 0. We have to go less than 0, so our answer is negative 2.4 degrees Celsius. That's our final answer. So if you did this, if you added 50 grams of sodium nitrate into 900 grams of water, tried to freeze it, this would be the new freezing temperature. Okay, let's try another one that's slightly different. This one is asking for molality. So this time we have to solve for molality. Little m. We have a sugar solution, C6H12O6, which causes the new boiling point to be 100.95 degrees. All right, so let's see what we have here. We have delta T equals KMI. Our change in temperature. What's our change in temperature here? It's not 100.95. It's only going to be the 0.95, because normally water boils at 100. It changed by 0.95, so put that over here as your change. Don't put the 100 in there. K, this is a boiling problem, so we're going to use 0.512. We're solving for molality. That's what the question says. And I, how many ions are in sugar? Well, because this is covalent, there is only one. It does not make ions. You drop one molecule of sugar in water, it's just going to float around as one molecule. It's not going to break apart. So here it's 1. Okay, now all we have to do is solve for little m. So this is just 1, so just divide both sides by 0.512. And little m becomes 1.85 little m. All right, so be aware that you may be asked to solve for things other than the change in temperature, usually not K, usually not I, usually either change in temperature or molality. And also, don't forget, covalent compounds only have one as their ions. Okay, here's one that gets really tricky, so put your thinking caps on. Same kind of stuff, you just kind of have to work around what you're given and figure out what's happening here. So it's asking us for grams. So whenever you see that, you better be thinking grams equals molar mass times moles. All right, so we're going to need that somewhere along the line. Let's put our formula here and plug in some numbers that we know. So this says a change of freezing. It's a freezing problem. How many grams of salt in 200 grams of water is needed to change the freezing point of water to -10? All right, our change in temperature here, the change was 10 degrees. It changed by 10 degrees. This was a freezing problem, so it got less than 0. But here we're just going to put 10 because that's how much it changed. The negative comes from the fact that we had 0 minus 10 gave us that, but the actual change was 10 degrees. K, this is a freezing problem, so K is 1.86. We don't know M yet because we're dealing with grams. We have to kind of figure this out first before we figure out what's going on over for M. I, we know we have 1, 2 ions. All right, let's clean this up a little bit. 10 equals 3.72 M. 1.86 times 2 is 3.72. Divide both sides by 3.72. And let's just say little m is 2.7. The formula for little m was moles per kilograms of solvent. So we have to solve for moles to really figure out how many grams we have. So we have 2.7 little m equals, it says 2 kilograms of our water. That 2 goes here. Here's moles on top. I'm using this formula to solve for moles. So it's cross multiply 2.7 times 2. 5.4 moles. And now we can go over here. 5.4 moles. Molar mass of sodium chloride is 58. So 58. There we go, 29.2 grams. So that's really about as difficult as it comes. We had to do a bunch of steps here. We had to use the molality equation. We had to use grams equals molar mass times moles. And of course, our main colligative property formula. And finally, here is the last way to figure out colligative property calculations. It's called the mole fraction. These are pretty easy. We'll just do one problem here. So a mole fraction, it's almost like a percent, except you don't multiply something by 100. It's just giving you a ratio of moles of solute to the total moles of everything that you have, solute and solvent. So this is a formula. If you want to figure out the mole fraction of your solute, this is your solute plus your solvent, and you just do this math. So here's a question. Antifreeze is added to radiators to decrease the freezing point of water so your car runs when it's cold outside. That's why antifreeze is in your car, because it drops the freezing point of water to less than 0. This way your cooling system doesn't freeze in the winter time. So what is the mole fraction if you have 1.25 moles of antifreeze and 4 moles of water? So here is your solute. It's the antifreeze. For some reason, the symbol for mole fraction is X. I don't know why. So 1.25 goes up top. On the bottom, you're going to put the 1.25 plus the 4. So this is going to be 1.25 divided by 5.25, and you're going to get 0.24. This is just a ratio based on moles. Very simple calculation. That's really all there is to it. If you wanted to figure out the mole fraction of the water, you could also do that. You could put, this time you put the 4 on the top from the water, and then the total 5.25 on the bottom. If you did this math, you'd come up with 0.76. This is for the water. This was for the antifreeze. Well, if you add these numbers together, you're going to get 1, because this is a ratio. It's a ratio number. That's it. That is the end of colligative properties.